Hi, my name is Mark Arinaitwe from the University of North Dakota, and I will be discussing my paper titled Conceptualizing Trustworthiness of AI Systems. The basic overview of the presentation is as follows. We will begin with the motivation of the paper. We will then briefly introduce trustworthiness in AI and what it means. We will then introduce the trustworthiness conceptual tree, which consists of three main parts. These are key trustworthiness attributes, trustworthiness factors, and methods to achieve trustworthiness. AI is transforming industry and everyday life and enabling new capabilities, and can be used in decision making, automation, and analytics across many domains, such as finance, healthcare, transportation, hiring, and more. However, this reliance on AI also introduces serious risks, things like biased decisions, privacy breaches, and harmful or unsafe outcomes when systems fail in surprising ways. So we need AI systems that can be justifiably trusted by both users and society, not just because they look impressive, but because their behavior is reliably aligned with what we intended them to do. So this is what we mean by trustworthiness. It's the system's ability to behave as intended and in line with stakeholder values, even as it interacts with the real world. To make that more precise, we need to separate the idea of trust from trustworthiness. So trustworthiness, we can define it as an objective quality attribute of an AI system. And it's not just whether a user happens to feel trust or not for it. An AI system is trustworthy if its intrinsic properties actually warrant trust. For example, if it's robust, fair, transparent, and so on. This is related to the classical idea like dependability. But for AI, we have to take into account and extend this concept to and include other factors and attributes such as fairness, value alignment, and socio-technical impacts such as manipulation or misinformation. So our goal here is to design and evaluate AI systems so that these properties are present to a degree that genuinely justifies trusting them. So to help with that, we propose a three-pillar framework or a trustworthy conceptual tree. We organize trustworthiness around three connected elements. First, the factors, and these are properties of the model and data that can either threaten or support these attributes. These include things like opacity, bias, or concept drift. Second, these concerns or attributes, things we want from a trustworthy AI system, like accuracy, fairness, robustness, and transparency. Third, we have the concrete techniques and processes we can use across the AI lifecycle to manage those factors and achieve the attributes we care about. Taken together, you can picture this as a conceptual tree of trustworthiness attributes of a system, the factors that affect these attributes, and methods we can deploy to control these particular factors. So let's start by looking at the factors and what actually affects trustworthiness. We use the words factors to mean characteristics that can undermine one or more of the trust attributes we just mentioned. We can group these into two broad classes. The first group is model-related factors, things like opacity, misalignment, that arise from how the model behaves and is deployed. The second group is data-related factors. This includes bias, data poisoning, and concept drift, all of which come from how data is collected, labeled, and evolves over time. So by understanding these factors, we can better target our mitigation strategies instead of just hoping a single metric like accuracy would be enough. So we'll start with the model-related factors. The first is opacity, and is related to how the AI behaves like a black box when its internal logic is hard or impossible for humans to follow. This opacity directly reduces transparency and accountability because we can't see or explain what the system is doing. It also means users often can't understand or effectively contest decisions, which undermines confidence in governance. The second factor is robustness, how easily the model is fooled by carefully crafted perturbations into its input. In many systems, very small changes to the input can cause large and unexpected errors in the output. That harms the reliability and safety of the system, especially in open environments where inputs can't be perfectly controlled. Two or more model-related factors are misalignment and oversight. These next two are more about goals and governance. Misalignment occurs when the system's goals or optimization criteria don't actually match users' intent or human values. In this case, the system can be very competent at optimizing the wrong objective, which is not what we want. That can lead to unintended or even harmful outcomes, even though the system is doing what it was told to in a technical sense. Then we have lack of oversight. This is where there's no clear human in the loop or governance structure, no one actively supervising how the system is used. Without audit trails or defined responsibility for harm, it becomes very hard and difficult to hold anyone accountable when something goes wrong. On the data side of factors, we see a different set of threats. First is bias. This is a systematic prejudice in the data because it is skewed or not representative of the populations we care about. That bias can show up as unfair decisions for certain groups, or even if nobody explicitly coded in the discrimination. Next is data poisoning, where an attacker deliberately manipulates the training data. By inserting carefully crafted examples, they can degrade performance or insert malicious behavior into the model. Privacy violations, these happen when personal data is overcollected, misused, or accidentally leaked by the AI model. And finally, concept drift. This is how the data distribution changes over time during the AI's deployment. So this figure gives a visual overview. On one side, you can see we have the factors, and on the other side, we have the attributes. And these arrows show how each factor connects to one or more attributes of trustworthiness, making explicit which parts of trustworthiness are threatened by which issues. So you can see on the model side, we see factors like opacity, misalignment, adversarial vulnerability, and lack of oversight. These are things we just talked about. Properties of the model and its deployment can erode transparency, safety, and accountability. On the data side, we have bias, data poisoning, privacy violation, and concept drift. These arrive from how the data is collected and evolve how the data evolves over time and can directly impact fairness, reliability, privacy, and accuracy. However, the key point of this figure is that each factor undermines a specific trustworthiness attribute. For example, bias primarily attacks fairness, data poisoning threatens reliability and robustness, privacy violations impact privacy, and misalignment cuts across safety and value alignment. Having such a mapping helps us be more systematic, and once we identify which factors are present in a given system, we can know which attributes need attention and which methods to prioritize for that particular system. We now turn to the attributes that make an AI system trustworthy. Here we identify a set of core attributes. These include accuracy, robustness, safety, fairness, transparency, explainability, accountability, privacy, and controllability. These attributes are interrelated and sometimes overlapping. For example, transparency supports accountability, and robustness contributes to safety. Any weakness in any of these tends to reduce overall trustworthiness, so it's not enough to just optimize just one metric. So accuracy. This is the ability of a system to produce correct outputs for the task it's meant to solve. We usually measure this using error rates and other performance metrics, and we care about consistency across relevant conditions. Robustness is the ability to maintain performance when conditions depart from the ideal, when inputs are noisy, unusual, or adversarial. That includes everyday noise, natural shifts, but also adversarial inputs crafted to confuse the model. A trustworthy AI system usually needs a balance, strong enough accuracy and sufficient robustness. However, an increase in one tends to lead to a decrease in the other. Safety means the system operates without causing unacceptable harm. That includes not just physical harm, but also psychological, economic, and even societal harm. It is closely tied to the principle of non-malfeasance, and in many cases extends to sustainability when we consider long-term impacts. Fairness is about making decisions that are impartial and equitable. In practice, that means we avoid systematic disadvantage for protected or vulnerable groups unless there is a very strong justification for it. Two other highly linked attributes are transparency and explainability. Transparency and explaining essentially help us see what the system is doing and why. Transparency means being open about how the system is built and evaluated. This covers the algorithms used, data sources, the evaluation protocols, and known limitation. Explainability, on the other hand, focuses on providing understandable reasons for specific outputs. For example, why a particular decision was made by the AI. Those explanations might be local or global, but the key is that humans can interpret them. Together, transparency and explainability support debugging, external scrutiny, and user acceptance and understanding of AI systems. Now we can move on to accountability and privacy and controllability. So accountability means having clear assignment of responsibility for outcomes. To make that work, we would need logs, documentation, and government structures so that people can investigate and correct issues. Privacy is about protecting and appropriately using personal data. That includes meaningful consent, data minimization, and technical safeguards, such as access control and privacy-preserving methods. Controllability refers to meaningful human oversight and intervention, which means that humans should be able to monitor the system, override its decisions, or shut it down when needed, especially in high-risk applications. Now we map different methods to the concerns and factors we've identified. For example, we have oversight and governance mechanisms that strengthen accountability and controllability. We have opacity reduction mechanisms that help address the black box nature of models. We have perturbation tolerance and robustness methods to handle noisy or adversarial conditions. We have data processing and privacy-preserving techniques that increase fairness and privacy. And finally, we have sustainability and efficiency mechanisms that address resource and environmental concerns. And I'll briefly walk through each of these methods with some concrete examples. So, oversight mechanisms. These help ensure AI don't operate without human supervision. For example, runtime monitoring continuously tracks the system's behavior in production and flags any out-of-bound behaviors or anomalies. Documentation and transparency artifacts, such as model cards, describe intended use, performance, and limitations, helping others understand and audit the system. Logging record inputs, outputs, and key internal signals so, so that we can later reconstruct what happened and why. Safe interruptibility, this ensures that we can pause or stop the system without causing additional harm or having the system fight back against any interruption. And human in the loop, these designs help humans be involved in critical decisions, either by requiring approval from a human or by making overriding mechanisms easier to use. To tackle opacity, we have several complementary strategies. First, post hoc explainability methods like LAM and SHAP provide feature attributions or using simple local models that help us understand individual predictions. Second, we can sometimes choose inherently interpretable models, such as decision trees or rule-based systems, when the problem and performance constraints allow for it. Third, saliency and visualization techniques can highlight which parts of the input were most influential. For example, which pixels in an image or token were most important in making a decision for the AI. Fourth, example-based explanations retrieve similar past cases to give users a concrete sense of why the system made a particular recommendation or decision. Finally, self-explaining models are designed to output explanations alongside predictions as part of their architecture. Now we move on to data processing and handling. Data augmentation can diversify the training data, improve generalization, and sometimes reduce bias by including more varied or edge case examples. Differential privacy methods, these can mathematically bound the influence of any single data point on the model, reducing the risk of leaking individual information. Federated learning, this helps us train models without centralizing raw data, and only model updates are shared, so personal data can stay on local devices or servers. Encryption and secure multi-party computation allows us to operate on encrypted data, limiting who can see sensitive inputs, even during training or inference. And synthetic data can mimic the statistical properties of real datasets without directly exposing real individual records. And here are some representative techniques on the robustness and sustainability side. Adversarial training explicitly teaches models to withstand perturbed inputs by including adversarial examples during training. Robust optimization focuses on worst-case performance within some uncertainty set, instead of only optimizing average performance. On the sustainability side, green AI approaches can prioritize energy-efficient architectures and training regimes, and not just raw accuracy. Techniques like model compression, pruning, and quantization can shrink model size and reduce compute requirements. And batching tasks and transfer learning help reduce compute and carbon footprint by reducing knowledge instead of training from scratch every time. To summarize the main ideas of this paper, similar to dependability in the classical computing, which encompasses a set of attributes that together ensure an AI system can be justly trusted by its user and its society. This paper provides a conceptualization of trustworthiness in AI systems and understanding its attributes, the threats that impede them, and the means to achieve them. Like dependability, trustworthiness is a multi-dimensional quality attribute of AI systems, not just a single number. and we can organize it into concerns, factors, and methods. These factors include model, the data issued, such as opacity, bias, data poisoning, concept drift, and misalignment. The attributes we care about, these include accuracy, robustness, safety, fairness, transparency, explainability, accountability, privacy, and controllability. And the methods are the technical and governance mechanism we apply across the AI lifecycle to manage those factors and achieve those attributes. And that's all I have for this presentation. Thank you very much for listening.